Welcome to this tutorial on Newton's second law and force components. Today, we'll look at 5 practical examples that illustrate how to resolve forces into components, compute net forces, and find accelerations. Let's start by recalling Newton's second law of motion. It states that the net force on an object equals its mass times its acceleration. Remember that force and acceleration are vector quantities, which means they have both magnitude and direction. When working with multiple forces at different angles, we need to resolve them into components, typically along x and y axes. For a force F at angle theta, the x component is F times cosine theta, and the y component is F times sine theta. Now, let's jump into our first example. Example 1. A 4-kilogram block is pulled by 2 ropes. Rope A pulls with 20 newtons at 0 degrees above the horizontal. Rope B pulls with 15 newtons at 60 degrees above the horizontal. There is negligible friction. What is the block's acceleration? First, we need to resolve each force into its x and y components. For force A, which is at 0 degrees to the horizontal, the x component is 20 times cosine of 0, which equals 20 newtons. The y component is 20 times sine of 0, which equals 0 newtons. For force B at 60 degrees, the x component is 15 times cosine of 60 degrees, which equals 7.5 newtons. The y component is 15 times sine of 60 degrees, which approximately equals 12.99 newtons. Next, we calculate the net force by summing the components. The net force in the x direction is Fax plus Fbx, which equals 20 plus 7.5, giving us 27.5 newtons. The net force in the y direction is Fay plus Fby, which equals 0 plus 12.99, giving us 12.99 newtons upward. Since the block stays on the table, there must be a normal force that cancels out the net vertical force. So the motion is only horizontal. Finally, we can find the acceleration using Newton's second law. The acceleration equals the net force divided by the mass, 27.5 newtons divided by 4 kilograms, which equals 6.875 meters per second squared. So the block accelerates to the right at 6.875 meters per second squared. Let's move on to example 2. A 10-kilogram box rests on a 30-degree incline. The coefficient of kinetic friction is 0.2. Find the box's acceleration down the slope. In this problem, we need to resolve the weight into components parallel and perpendicular to the incline. The weight is mass times gravity, which is 10 times 9.8, or 98 newtons. The parallel component, which is down the slope, equals weight times sine of 30 degrees. That's 98 times 0.5, which equals 49 newtons. The perpendicular component, pressing into the incline, equals weight times cosine of 30 degrees. That's 98 times 0.866, which equals 84.9 newtons. Next, we calculate the friction force, which acts up the slope. Friction equals the coefficient of friction times the normal force. The normal force equals the perpendicular component of weight. So, friction equals 0.2 times 84.9 newtons, which equals 16.98 newtons. Now we can find the net force down the slope. The net force equals the parallel component of weight minus the friction force. That's 49 minus 16.98, which equals 32.02 newtons. The acceleration equals the net force divided by the mass, 32.02 newtons divided by 10 kilograms, which equals 3.202 meters per second squared down the incline. Moving on to example 3. A 5-kilogram mass hangs from a rope. The rope is pulled so that the mass accelerates upward at 2 meters per second squared. Find the tension in the rope. In this problem, we have 2 forces acting on the mass, tension upward and weight downward. The weight is mass times gravity, which is 5 times 9.8 or 49 newtons. Using Newton's second law, the net force upward equals tension minus weight, which equals mass times acceleration. That's 5 kilograms times 2 meters per second squared, which equals 10 newtons. Finally, we can solve for the tension. From our equation, tension equals net force plus weight. That's 10 plus 49, which equals 59 newtons. Notice that the tension is greater than the weight. This makes sense because the mass is accelerating upward, so the tension must overcome both the weight and provide the force needed for acceleration. Let's look at example 4. A 3-kilogram cart on frictionless rails is pushed with a force of 10 newtons east and a force of 6 newtons north. Determine the cart's acceleration vector. In this problem, we have two perpendicular forces. The components are straightforward. Fx equals 10 newtons and Fy equals 6 newtons. We can calculate the magnitude of the net force using the Pythagorean theorem. Square root of 10 squared plus 6 squared, which equals square root of 136, or approximately 11.66 newtons. The direction is tan inverse of 6 divided by 10, which is about 31 degrees north of east. Now we can find the acceleration using Newton's second law. The x component of acceleration equals Fx divided by mass, 10 divided by 3, which equals 3.33 meters per second squared. The y component of acceleration equals Fy divided by mass, 6 divided by 3, which equals 2 meters per second squared. So the acceleration vector is 3.33 I hat plus 2 j hat meters per second squared, with a magnitude of 3.87 meters per second squared at 31 degrees north of east. Let's finish with example 5. A 2-kilogram pendulum bob swings so that the string makes 45 degrees with the vertical. At that instant, its speed creates a net acceleration toward the pivot of 4 meters per second squared. Find the tension in the string. In this pendulum problem, we need to resolve the weight into radial along the string and tangential components. The weight is mass times gravity, which is 2 times 9.8 or 19.6 newtons. The radial component, which is toward the pivot, equals weight times cosine of 45 degrees. That's 19.6 times 0.707, which equals 13.86 newtons. The tangential component, which tries to pull it back to the center, equals weight times sine of 45 degrees, which also equals 13.86 newtons. The radial net force provides the centripetal acceleration. The net force in the radial direction equals tension minus the radial component of weight, which equals mass times the radial acceleration. That's 2 kilograms times 4 meters per second squared, which equals 8 newtons. Finally, we can solve for the tension. Tension equals the radial net force plus the radial component of weight. That's 8 plus 13.86, which equals 21.86 newtons. Note that the tension must be greater than the radial component of weight to provide the centripetal acceleration needed for the pendulum's circular motion. Let's summarize what we've learned from these 5 examples. When applying Newton's second law, always 1. Identify all forces acting on the object. 2. Resolve forces into components along appropriate axes. 3. Apply F equals ma for each direction. 4. Solve for the unknown quantities. With practice, you'll become comfortable using these techniques to analyze more complex physics problems involving forces and motion.